I knew you were not going to pause the video, so I just made a different video. Okay, so let's check our answers. Let's make sure we got it right. So that would go like this. Okay, so the object with the greatest moment of inertia would be the hoop. That means this one has the greatest resistance to rotation or to stop rotating. In the thin rod center, but what that means is you're rotating a rod, you can think of a meter stick, from its center. So that's because it has less moment of inertia. What we're saying is easier to rotate a meter stick when you hold it from the center, from the 50 centimeter mark, rather than rotating it from the end. If anyone has practice, or I don't know how you call it, but doing the flag thing, it's easier to spin the flag from the center than from the end. Okay? So now I want you to think about this question. Oh, before we do that, the way to get this done is just look at the fraction. Right? Which one has the greatest fraction? The hoop, because it doesn't have a fraction, meaning there's a 1 here, and 1 is greater than any fraction. The second one would be the shell, because it has 2 or 3, that's 0.66, and that's greater than the cylinder, because for the cylinder is 1/2. So that's how you do it. So now the next question. It says, if a ring, a disc, and a sphere of equal mass and radius all were in a race down a ramp, which item would reach the bottom first? Why? A ring is a hoop, same thing. Disc, you can think of a very flat cylinder, and then a sphere, well, you know what that is, solid sphere. Same mass, same radius, okay? Discuss which one would get to the bottom first and why. Okay, so in this case, I'll show you a video and then check your prediction. As you can see, it was the sphere. Let's think why. If they have the same mass, same distance from the axis of rotation, what's changing? Well, the shape, right? Moment of inertia is based on the shape, and that gives a different distribution of the mass. Although overall they have the same mass, the distribution of the mass is different. For the sphere, is very uniform because it's solid. Furthermore, you can just look at the moments of inertia. The sphere has the smallest number when you compare that to the disc or cylinder and the hoop. Let me show the video again. Notice how the hoop reaches the bottom last because it has a greater moment of inertia. It doesn't want to rotate. It's resisting the force of gravity. Then cylinder, second place, and then the first place would be the sphere because it doesn't really care. It shows no resistance to rotation by gravity. Okay? So let's state our why. Okay, less resistance to rotation. Now let's consider a hoop, a ring, in a uniform cylinder of equal mass and radius, competing down a ramp. Well, we already know that the disc will win, okay? Now let's write a general formula for the conservation of energy for both items. So let's draw an inclined plane and then one of the objects. So there we have it. Before we release, let's think about the energy right before we release. Well, there's a height. Let's just call it h. Height h. And they have mass, so that means they have gravitational potential energy. When we let the cylinder and the hoop roll down the incline, they're going to gain kinetic energy. What type of kinetic energy? Well, it'll be both, right? Because it's rotating and also moving linearly. Linearly from the top of the ramp to the end of the ramp, and of course it's rotating. So now we'll call this one kinetic energy total. And kinetic energy total is going to be the sum of both kinetic energies, rotational and translational. Now let's plug in the formulas we know. We know all three formulas. There we have it. And if you think about it, they have the same mass, so I don't have to have m1, m2. What would change is the linear velocity and the angular velocity. Okay? So the one that wins, meaning the one that reaches the bottom first, should have a greater linear velocity, and the one that loses should have a greater angular velocity. We'll see why. So we can say that this formula applies for both objects. Okay, now I know it says determine the velocity of the hoop at the bottom of the ramp using energy conservation. I'm going to show you how to find the velocity of the cylinder at the bottom of the ramp using energy conservation, because this one's slightly more difficult. Okay, so we're going to take the same equation, same formula, but now let's define the velocity for cylinder. I'm going to call it VC, and then angular velocity for cylinder, I'm going to call it omega c. So those are my quantities. That means the equation will look as follows. I also needed to define the moment of inertia because they have different moments of inertia. Where can you find that? Well, you go to the top of the page, and then here are the quantities, the experimental expressions or formulas for moment of inertia. Okay? All right. Now, let's see. We cannot really cancel anything, not the mass, because this one doesn't have mass. Well, at least not yet. So what we'll do is we'll replace the moment of inertia cylinder with the actual formula and just get it from the top of the page. Okay, so the only thing I did is I replaced the moment of inertia, I cylinder, with 1/2 mr squared from the top of the page. Now let's clean it up. Well, I can simplify this when I can get rid of the parentheses. I'm multiplying two fractions. That's numerator times numerator, denominator times denominator. Okay, so now let's deal with this omega, because I don't want to have it there, okay? I just want to have an expression for velocity. We know how to find velocity in terms of, angular velocity in terms of linear velocity using tangential quantities. So from the very, very first set of notes we took, which is this page, where was it? This one, remember? From that one, we can get that omega is equal to velocity, linear velocity, divided by radius. So we'll use this formula with the cylinder, and then it'll look as follows. So the radius is the distance from the axis of rotation. So that's what we have, capital R. And then the velocity of the cylinder is the velocity of the cylinder, okay? Now we're going to distribute the square to get, and also we can cancel the mass, because now the mass is repeated everywhere. Now we can cancel r squared with this r squared. And I keep working on the side, and I'll get the following. Okay, so now notice how these two expressions have v squared, so I can just factor it out. And I need to combine 1/2 and 1/4. What I need to do is get a common denominator. I'm trusting you can do that. So then we'll get the following. Now that we have the common denominator, we just combine 2/4 and 1/4. Let's rewrite this one. Well, actually, no, we don't have to rewrite it. Now let's get rid of that fraction because we're solving for a v, which is multiply times the reciprocal. I'm going to use the reflexive property. That just means change the order. So the one that was on the right, I put it on the left, and so forth. So now we just get rid of that square by taking the square root. So the velocity for the cylinder is the square root of 4/3 times acceleration of gravity times the height. I think it's cool how we started with this equation and we ended up with this simple formula. Now what you need to do, you need to do the same thing, follow the same process, but now do that for the hoop. This one's easier, I promise. Also be mindful that because the cylinder gets to the bottom first, this quantity should be bigger than the result you get from this one. So the velocity for the hoop should be less than this. Okay? Once you're done, I need you to complete these questions. They're super easy. They're conceptual, based on your results from these two.